Hello everyone, this is North America Math Con. Let's go. On this week, we are going to talk about the logarithmic equation and exponential equation. Before we talk about the logarithmic equation, it's very crucial to understand what the exponential law is. Let's first talk about the exponential. Exponential is any number that is in the form of a to the power of x, which in this case is denoted as a times for x different times. So for example, let's say we have 5 to the power of 6, which is 5 times 5 times 5 times 5 times 5 times 5, which in this case is times 5 for 6 different times. The result is going to be 15625. Okay, so let's try another example. What's 3 to the power of 5? So 3 to the power of 5 is 3 times 3 times 3 times 3 times 3. Okay, 243. So after we know this is 243, let's then talk about we now know the way to calculate the exponential. Let's talk about some basic formula. So first of all, this one. A to the power of b to the power of c. It is equal to a to the power of b to c. Why? It is because that the original equation we do a to the power of b times a to the power of b times a to the power of b for c consecutive times, which is times a for b times for c consecutive times, which in this case is b times c times, which is b c times. So it would be a times, so it will be times a for bc times, so it is this. So basically you are very confused. If you are very confused about this, I'm going to make another, do like this, right? It will be like this, right? So what we can do is that we first do like this. Right? So it will be like this. Okay, so it will be like this. 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 12. Let's see. So for this example, this is the second formula that you need to learn. So why would be that? So basically you times a by b times, and then you times a for c times, so times a for b plus 3c times. Right? If you are more confused, let's give you an example to show that. For example, a to the power of 3. Right? It would be a times a, which times a to n, a to n, a to n. It would be a to the power of a. So it's you times a for 3, you times 3a and then you times 5a, so it would be a to the power of 8. The next thing would be this. This one is that when you times a for total number of c, for a total number of c, a's will be cancelled and only b minus c a's will be left. So let's give you an example. A to the power of 6 to the minus a to the power of 3. Right? So 1a is cancelled, 2a is cancelled, 3a is cancelled, right? So the last number will be only 3. So it would be a to the power of 6 minus 3 is equal to a to the power of 3. And the last formula you are going to learn is this. A times b to the power of c, which is a to the power of c times b to the power of c. Why? Because ab times ab times ab times ab, it will be a times b, something like this. The next thing we want to learn is that anything to the square of 1 is a, and anything to the power of 0 is 1. Why is that? Because a to the power of 0 can rewrite 0 as right? So it's a to the power of x minus x, so it's a to the power of x divided by a to the power of x is 1. The next one, what is a to the power of negative x? So a to the power of negative x is equal to a to the power of 0 minus x. So this is equal to a, right? So it would be 1 over a to the power of x, right? The next thing we are going to talk about is how it is defined. So it's 4 to the power of 7 divided by 2 to the power of 6, like this, right? The 4 to the power of 7, so the first thing we do is that we use this rule, this one. So it's 2 to the power of 2 to the power of 7. So it's 2 to the power of 14 divided by 2 to the 6. So this thing 2 to the 2 power of 2 times 7. So it is 2 to the power of 2 times 7 is 2 to the power of 14. So it's 2 to the power of 14 minus 6, so 2 to the power of 8, which is very important. And then there's another rule that I forgot to write about it. 2 to the power of a divided by b, right? So it's equal to this, squared b 2. So it's 2 to the power of 2 divided by b. I don't know why it doesn't work, so it's like this, and then you times this by a. It will be something like this. So this formula will be like this. Hey? It doesn't work, so it will be like this, right? An example would be 2 to a to the power of 5, like this. So it's will be like this for this formula, and then we change it into this to the power of 5, so it's 2 to the power of 5, which is 32. Now let's talk about the last digit rule, which is very important because this is an easy way for you to decide last digit. So basically you can decide this through the unit digit and exponent. This is a complete table, but I'm going to tell you how to deduce this table. So basically we know. Let's first talk about why the exponent is divided by 4. It's really hard to say without calculating them, so let's start from 1. 1 to the power of 0 is 1, right? 1 to the power of 1 is 1, 1 to the power of 2 is 1, 1 to the power of 3 is 1. So 1 to the power of everything is 1. And then this one. So basically we again need to talk about why is it like why unit digit needs to be important. So let's say x1 times x1. So it would be x1, right? Then times x1 is equal to x1. So the unit digit is always like, no matter what the 10th digit is, times x1. So it's x1, right? So no matter what you, like no matter what the 10th digit is, the unit digit is always going to be 1. So we know then it is important of the unit digit of the base. And then for the exponent, we then can talk about 2. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5, it's equal to 16 times 2. Right? 32. 2 to the power of 6 is equal to 32 times 2 is equal to 64. 2 to the power of 7 is equal to 64 times 2 is equal to 8, right? And then 2 to the power of 8 is equal to 128. Sorry, this one would be 64 times 8 is equal 2 is equal to 256. So as you can see, it has a clear pattern of 2, 4, 8, 6. We then are going to do the same thing for 3. So let's start with 3 to the power of 1. So 3 to the power of 1 is 3, 3 to the power of 2 is 9, 3 to the power of 3 is 27, 3 to the power of 4 is equal to 81. So the first digit is 3. The unit digit of the first 4 cases is going to be 3, 9, 7, 1, respectively. What you do then is that you times those numbers again. 3 to the power of 5 is equal to 243. 3 to the power of 6 is equal to 729. 3 to the power of 7 is equal to 2187. 3 to the power of 8 is equal to 6541. 61, sorry. So as you can see, and then you time it by 9, you'll find that the last digit again becomes 3. So you can see that it has a recursive pattern, 4. Then I talk about 4. Let's talk about 4 then. We then cut it off, and then it will be 4 to the power of 4, 4 to the power of 2, 4 to the power of 3, 4 to the power of 4, 256, 4 to the power of 5, 1024. Right? So as you can see, no matter how much you times 4 by, the last 2 digits are always going to be 464646, right? So this wouldn't be that their pattern is 4646. For 5, it's relatively a bit simple because no matter how you time it, like the last digit is always going to be 5, right? 5 times 5 is 25, 25 times 5 is this, 125 is equal to this, sorry, is equal to this, right? So it will be 5555. We are then going to talk about 6. 6 is just simply this. Why? Because if you do 6 times 6, it will be 36. 36 times 6 is equal to 216. 216 times 6 is equal to 1296. 1296 times 6 is equals to 7776. So As you can see, no matter what the exponent is, it will always be equal to 6. Then let's talk about the 7. Seven times 7 is equal to 49. 7 to the power of 1 is equal to 7. 7 to the power of 3 is equal to this. 7 to the power of 4 is equals to 343 times 7 is equals to 2001. And then, if you time it by the next 4 successive number again, you will find out that they fulfill the 7931 repeated pattern again. It's equal to 823543, and then you time it by 9 again, right? And then to go back to 7 again. So as you can see, it has a pattern of 7931, 7931. So it works. Okay, so let's now look at 8. 8 is 6842. I'm not going to calculate again. You can just use the way that I do to try calculate the last 4. Oh, sorry. And then it's 1919. So you can use this table to help you find any number that you want, which the entire table just simply looks like this. Okay, so we are then going to do an example. So we are required to find the last digit of 999 to the power of 873. We can use the chart above to find it. Look at this. So basically this has a right unit digit of 9 for the base. And then the exponent 874 when divided by 4 has a remainder of 2. So therefore 999 to the power of 874 has a unit digit of 1. Due to that, 9, right? 9 is here, 2 is here. So 98, 92 is 1. 9, right? 9, 2, 1. We are then going to quickly talk about the exponential equation drawn on the graph, because it will usually be required for you to draw it. So basically you can see there are 4 different conditions. The first one is a to the power of x. This cases require both a and x to be larger than 0. So it goes up, right? Goes up. The next thing is a to the power of negative x. So basically a is still positive. Negative x is x is also positive, but it's in the form of negative x. The second thing, negative a to the power of x, similar to this one, except it is reflected across the x-axis, and this one is negative a to the power of negative x. If it is a, if it is actually for negative a, it will be something like this. It will just like be in a curve. In a curve that is, in a wave, you know, that will like have its magnitude increases for every single going down and up. So for example, the first one may just go to the height about the 2 meter, the second one will go to the height of negative 4 meter, the third one will go to the height of 8 meter, the fourth one will go to the height of negative 16 meters, till like this, something like this. So it will be a pretty weird graph. Here, we come to the end of our lesson about exponential. In the next video, we'll be talking about the logarithms. Here we come to the end, and I hope you have learned a lot. See you next week. Bye bye.